Hey team, chemistry coach coming at you. Let's polish off this chapter looking at some electron configuration definitions and examples. So we did the rules in the last video, and you got to know the rules to do it. And the better you know the rules and the Aufbau process and buildup of energies, these things are cakewalk. You will love these questions on quizzes and exams. And oh my gosh, they give you so much information on the chemical behavior of a particular element, a magnetic behavior. You can predict the ions it prefers, if it reacts to form an ionic compound. It explains a lot about the periodic table that Dmitri Mendeleev didn't know about at the time. Just kind of fell into place. Really cool. You got to know how to do electron configurations. All right. So a couple definitions that are going to be really important for us. Valence versus core shells in electrons. So remember, you got n equals 1, n equals 2, n equals 3, n equals 4. Well, the highest value, the higher n you get, if this is the nucleus, n equals 1, 2, 3, 4, 5, the higher the n value is, the larger the orbital, the further away it is. So that highest n shell that goes all the way around the nucleus is the furthest shell away from the nucleus that still has an electron in it. Would it make sense that if I have an atom here and an atom here and they come together now, right? The nuclei aren't going to hit. It's going to be the outermost electron shells, the valence shells, that overlap, and that's where the chemistry happens, right? So valence electrons is any electron found in the highest n level. Doesn't matter if it's an S or a P, it doesn't matter, right? They all have, so say 6 is the highest number. You have some in 1, 2, 3, 4, 5, but you got a couple in 6. 6 is the furthest one out. It's the highest n value, right? It's the highest energy. That's going to be, those are the electrons involved in the chemistry, and you just count them all up. That's in that high. So if you have like a 6s2 and a 6p1, well, that's a total of 3 electrons in there. Okay? Those are the ones involved in the chemistry. So real critical. Ultimately, what we're after is not necessarily the overall electron distribution. We're really interested in how many electrons, after you sprinkle your electrons into all the available lowest energy orbitals to get the ground state, the lowest energy configuration, how many are in the valence shell? That is really what we're after. And you're going to see some interesting trends on the periodic table. All right, well, what if it's not in the outermost shell? Oh, it's in an inner shell. Those are called core electrons, typically not involved in the chemistry. Very commonly, they're filled as well. So you're going to see some shortcuts we can do where we pop some of these core electrons in as a noble gas in a bracket. We call it a noble gas core configuration. It's kind of a shortcut, right? So inner electrons are the core electrons, outer electrons are the valence electrons. All right, rock and roll. Here we go. Let's look at the different types of notation. So really there's 4 types. There's the really long, bulky way that tells you everything. There's the normal electron configuration. There's the shortcut, and then there's the orbital box diagram, right? So 4 different ways. So the first way I'll mention, but I don't know anybody truly that uses it, but I want you to appreciate how bulky this is and how it's not really necessary per se. So this is called the expanded spdf notation, right? Again, very rarely used. What we're going to do is actually show we're going to notate every single orbital. It's really a pain, and the only way you can do it is to know all of the orbitals. The dz squareds and all the f's. I don't even know all the f's. So really nobody does this, right? But I want to give you an idea how we collapse this to the next one would be a condensed SPDF. So this is kind of how you would use a typical notation. So you'd designate the principal quantum number n, right? Whatever its numerical value, n equals 1, n equals 2, 3, 4. And then, like we showed before, the letter represents the L value. So L of 0 is S, 1 is P, 2 is D, 3 is F. Right? So you got to know what those values are. So we're representing all the quantum numbers here. What we do is we do a subscript here to tell us which M sub L value it is. So if it's in the D set, is it the XY, the XZ, the YZ, the X squared minus Y squared, or Z squared? If it's P, is it PX, PY, or PZ? Right? S doesn't have one, right? It's only got one orbital. F, I didn't even tell you the F, so we couldn't even do the Fs. And then we use the superscript to tell us how many electrons there are in each orbital. And that would be a 1 or a 2. If it's a 0, why would you even write it? All right? So we can say, and we can, because of the Pauli exclusion principle, have up to 2 electrons in an orbital. So that would be a 1 or a 2. You'll see in the condensed one later, we're just going to collapse all the orbitals into a subshell. right? It's a little bit easier that way. So let's do an example for this to show you how bulky and weird, well, not weird, just tedious it is. All right, if you guys are feeling up for it, see if you can do chlorine. So a neutral chlorine atom. So you just look at your periodic table and go, well, where's chlorine here? Okay, so we've got 17 protons, and we're assuming it's neutral chlorine atoms, so 17 electrons to distribute. All right, so we're just going to do the Aufbau process until we get 17 electrons done. If it was an ion, of course, if it was chloride, it would have one more electron, or 18. See what I'm saying? So you can do ions as well. You just have to know where the extra electron goes if it's an anion, or where it's removed from if it's a cation. That'll be a little bit more for later. So we got 17. So obviously the 1s is going to fill first. So let's do the 1s. All right, so we got 17, right? 17 electrons. So we're going to have the 1s sublevel, and there's only one orbital, and we can fit 2 electrons in there, correct? So there is no subscript for that because there's no specific orbital. There's only one orbital for the s. And that's full. So after the 1s is full, then we go to the 2s right here. So let's pop that in. There's no subscript for that, no specific orbital. And we can put 2 electrons from the Pauli exclusion principle in there. Well, that's only used 2 plus 2 or 4 electrons. We still got 13 left, right? So after the 2s is the 2p. And we can put 6 electrons in there. But there's 3 different orbitals, right? So we've got 2px, 2py, 2pz. Normally, we're not going to do that, right? In the next one, we're just going to collapse those in together. And we have 2 electrons in each one. See how it does each orbital? It just kind of, you don't normally see this. So we've got 2, 4, 6, 8, 10 electrons. We got 7 more to go. The 2p sublevel's full. That's full. So we go down to the 3s next. 3s. And that can fit 2 electrons. So 2, 4, 6, 8, 10, 12. We still got 5 more to go, gang. Thank you, Aufbau. So 3s is filled. Next, woo, we skip the d's and we go to the 3p's. And we got 5 of them in there. So let's draw the orbitals. So 3px, 3py, 3pz, and we have 5 electrons, right? So Hund's rule says 1 will go here, 1 will go here, 1 will go here. That's 3, and then 4, then 5. So we're going to get 2 there, 2 there, and 1 there. That is an expanded SPDF notation. 2, 4, 6, 8, 10, 12, 14, 16, 17. So if you add all the superscripts together, it should equal the total number of electrons, right? And we're just doing neutral atoms for now. Would you agree? You would look at that and go, "Ooh, that's just a pain in the you-know-what." Right? So this leads us to the next type of notation. Wouldn't it be nice if we could collapse all these down? See what I'm saying? So just take these, because they're all degenerate, so it really doesn't matter, and collapse those down into just the subshell because the orbitals are degenerate. So we can collapse these. And that gives us our next notation, which would be condensed SPDF notation. That's the second way to do it. It's one of the 4. Then I'll put a star next to this one. This is by far the most common way people do electron configuration. So if somebody says, draw the electron configuration for this, they're probably implying this one. So this is the most common. All right. So I'm out of space. So let's rewrite chlorine using the condensed SPDF, where we take the individual orbitals, boom, if they're degenerate, put them together. So we'll have 1s2, 2s2, 2p just in general with 6 electrons, 3s, 3p just in general with 5 electrons in it. The only problem with the SPDF, you don't know which electrons are in which orbitals and whether you have unpaired electrons or not. Can you see the unpaired one there? You won't be able to see that in the condensed SPDF. So you got to be able to see it differently in your head. So let's do that on the next board. All right, let's do the condensed SPDF for chlorine. So collapse all degenerate orbitals in a given sublevel into one notation. So for chlorine, we would just go 1s, put 2 electrons in there. The 2s, put 2 electrons in there. The 2p, put 6 electrons in there. 1, 2, 3, 4, 5, 6. The 3s with 2 electrons, and the 3p with 1, 2, 3, 4, 5 electrons. So this will look something like this. Fill up the 1s, then we go to the 2s. Put your 2 electrons in, then we go to the 2p. But we don't do the px, py, pz. We collapse them because they're degenerate, doesn't matter, and that fills up. So we put a 6 up there. So there's 6 electrons in the 2p sublevel, knowing that's filled. Then the 3s is filled, and the 3p has 5 electrons in it. And you're done. See how that works out? Let's do another one. Let's pick one with a transition metal in it. Let's do, say, zirconium. Ooh. Let's have some more fun. Let's do rhodium. Rhodium's number 45. That's not going to be fun. So do that for me real quick. Do rhodium, number 45. So I want you to pause this, take a second, and then do rhodium for me. All right? And I will go ahead and pop that up on the board here for you. Let me pause it. I'll write it up there nice and neat, and then we'll walk our way through it. All right. I know you did rhodium, but I changed my mind and changed it to zirconium, because rhodium's a weird exception to what the general rules are. So you would have wrote something down and it would have been slightly different. So general rule, the further down you get, the more exceptions happen to what we would think it is. And I'll talk about that in a little bit. All right, so let's follow through. So we've got the 1s, fill that up. The 2s, fill that up. The 2p, fill that up with 6. Then we go to the 3s, fill that up. 3p, fill that up with 6. And after the 3p, we go to the 4s. 1, 2, 3, 4. 4s, fill that up. See the 4s too? And then, remember, the d's are shifted, so here's our 3d. We fill all of those, so we get the 3d10. All right? And after 3d, we get the 4p. We get all 6 of those. So there's your 4p6. Then we come all the way down to the 5th row, right? So we fill up the 5s. There's your 5s2. And then if you want to get to zirconium, this is the 4d, 41, 4d2, a total of 40 electrons, right? And that's how you do the condensed SPDF. Pretty straightforward. Let me show you my personal favorite, which is a spin off the expanded SPDF notation where we actually show all the orbitals, but we're not going to label the individual orbitals. So it's kind of a combination of these two, but we're going to draw boxes to represent each individual orbital. It's called an orbital box diagram. My favorite, it gives you the most information. So let's do chlorine for that. All right, my personal favorite again, orbital box notation or orbital box diagrams. You can do it either way. I've heard it mentioned both do some orbital box notation or do some orbital box diagrams. I don't care, just orbital box. So we're going to show every single orbital as a box. We did this when we went over Hund's rule, right? And we're going to show each electron as a spin up arrow or a spin down arrow. And we don't need to, what's nice is we don't need to designate the notations of every single individual orbital like px, py, pz, or dxy, dyz if they're degenerate. We just show the sublevel as a whole. So it's a little bit nicer. So it's like the expanded SPDF notation without the pain. But it gives us similar information. This is really, really helpful. I always recommend you do this one. If it's not specified, if it just says draw the electron configuration, I recommend this one because it allows you to predict a lot of magnetic and chemical behavior most easily. You don't have to picture things in your head. So let's do chlorine, for example. 17 electrons, right? So what I do is I draw the basic sublevels. There's the 1s, 2s, 2p, 3s, and I just do the outfall process. Stick in 17 electrons, right? Lowest energy first. So the first electron goes there, but there's an energy gap between the 1s and 2s, so it pairs up. So there's 1, 2. So those are paired, and then they're magnetic fields would cancel, right? Well, here's number 3. There's a big energy gap there, so it's going to pair up. So those cancel each other out magnetically. That's 4. 5. Hund's rule says the next one goes here, 6, 7, just like that. There's a big energy gap there, so this next one's going to pair up rather than go in the 3s. So 4, 5, 6, 7, 8, 9, 10. Now it jumps up. 11. There's a big energy gap there, so it's going to pair up. 12. Now we go into the 3p. Right? So 2, 4, 6, 8, 10, 12, 13, 14, 15. Hund's rule, right? Now we pair it up. 16, 17. There's a big jump to the 4s, so we don't need to go there. Do you see the unpaired electron right there? The best thing about the orbital box diagrams is you can literally look at it and go, boom! These are all paired up, magnetic fields cancel, but hey, there's an unpaired electron there. So we have one unpaired electron. So we're going to see some interesting magnetic behavior because of that. And you can really see what the valence electrons are, can't you? What's the highest n level? 1, 2, or 3? It's 3. How many do we have in 3? That's the highest n level. And we have 1, 2, 3, 4, 5, 6, 7. We have 7 valence electrons. Right? The rest of these are core electrons. Do you see that? So really easy to get good information off of orbital box diagrams. I love them. The last one is a shortcut. It's called a noble gas core. Would you agree that these are all core electrons right here? That looks like core E. So these are your valence electrons. The outermost n equals 3, but this is n equals 2 and 1. So those are the inner ones typically filled. They're not involved in the chemistry. These are involved in the chemistry. So this has 7 valence electrons. So anything with 7 valence electrons would have similar chemistry. Wouldn't it be nice if we could just do a shortcut for this? Let's look at the periodic table. What goes up to fill the 2p? So there's 1s2, 2s2, 2p, right? Well, that would be neon. Correct? Would everybody agree? So 1s2, 2s2, 2p6 is neon. So if that's never going to change, couldn't we just write neon for that and just say, hey, maybe put some brackets, put neon in there, and then write the valence electrons? Yes, we can. That's the noble gas core. It's actually, you could apply it to the condensed or expanded spdf notation. It's called the noble gas electron configuration, right? Noble gas core electron configuration. You can apply it to any of the prior 3. It's the shortcut. I like the shortcuts. Let's do that. All right, let's apply the shortcut, right? So noble gas core electron configurations represent all core electrons up to the prior noble gas, and we're going to represent as the noble gas symbol in brackets, and that represents that whole electron configuration. You can think of this as a shortcut. Yay for shortcuts. We like those. It gets redundant doing the same stupid thing over and over and over. So let's say for strontium with 38 electrons. If you do the condensed electron SPDF notation, you get the 1s2, 2s2, 2p6, and you move all the way over. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Right? Well, what's the highest n level? 5. Do you see that? Would you agree there's 2 valence electrons there? And if we did the orbital box diagram, we would see 1 up and 1 down, and their magnetic fields would cancel out. But would you also agree that that whole mess up to 4p6, so the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, that would be krypton, wouldn't it? Do you see that? That's krypton. That's the noble gas prior to strontium. So what we do is just draw that in brackets. And then write, oh, Isn't that so much nicer? So this is the noble gas core. SPDF notation. That's a beautiful thing. It makes you just look at the prior noble gas, just put it in brackets, and then just do the rest. Oh, it saves you so much time, especially if you're doing like 94 electrons or something. Now we can also do it with the box diagrams. So we can do a noble gas core. Oh, if I could spell. Orbital box diagram. So let's rewrite that as an orbital box. Now we could do all the boxes for that, but if we do it as noble gas core, we draw krypton. That's the prior noble gas. And then we draw the 5s, right? And label it underneath and do the 2 electrons. Can you see those electrons are paired up? Hey, easy peasy. I like it. Let me show you a couple common weird ones where they're not quite what you think they would be. And we'll briefly talk about why. I'm going to overgeneralize a little bit. All right, one of the first exceptions that's pretty standard you'll run into is group 6 transition metals. Whoa, what's group 6? 1, 2, 3, 4, 5, 6. So your chromium, molybdenum, tungsten, and seaborgium. It's the 6th one over, right? So group, not using the A's and B's, so it's group 6. So the expected notation would be whatever n level it is, right? So this would be like 4s 3d. So notice if we had a 4s2, it'd be a 3d4, right? If we had a 5s2, it'd be a 4d4. So you see 1, 2, 3, 4 electrons over. So that's the expected notation if you follow the Aufbau process. Fill up the higher energy level S, like the 5s, and then you go to the 4d and pop in the 4. Well, not quite so simple. This is true for the larger ones, all right? So for tungsten and seaborgium, yes, you will see that behavior. Oh my goodness, what are we going to do? But for chromium and molybdenum, we see an exception. All right, so there's always exceptions to the rules, right? For chromium and molybdenum, what we find is instead of the S being filled and having 4 in the D subshell, one of those S electrons boop, pops over in the D shell to half fill the D shell. So you get the NS1 N minus 1 D5. So like a 4S1 3D5, a 5S1 4d5. So chromium and molybdenum are not what you would expect. So chromium, you would expect a 4s2 3d4, but you get a 4s1 3d5. That electron gets promoted in there. Let's take a look at why that happens real quick. All right, this is kind of the thinking. This will be true for the next set of exceptions as well. All right, so we got chromium. I drew the noble gas core orbital box diagram. So argon is prior to chromium. So if we look up chromium right here, so argon is the prior noble gas, and then we have the 4s and the 3d. Right? But I didn't put any electrons in there yet. Let's go ahead and put the electrons in. Right? So this is what we expect. Don't write this down. We would expect 4s2 3d4. This is actually what we find for the bigger ones, seaborgium and tungsten. But it turns out for most elements, some more symmetric electron distribution is better, right? So notice how this is full, so think of it as symmetric. This is not even half full. It's kind of off. It's just got this gaping hole. So what happens is it turns out a lower energy would be to promote that one up there, so that electron doesn't go there. So you avoid the spin pairing energy and you pop it over there. So now see how symmetric that is and symmetric that is? So half-filled D subshells are lower energy. They're a little bit more symmetric, I guess you could think. This is also going to be true for filled subshells. We'll do. So that's also true for filled D subshells. We're going to find that can also happen a little bit in the F. I'm not going to do any electron configurations that fall within the F. If they're full, that's one thing, but not partially filled F subshells, because you get a lot of exceptions like this as well. But we'll stick with the D. See that? So this is much more energetically favorable, and only if you're one away. Now, as you get further from the nucleus, it might promote two of them. It gets kind of weird. We'll keep it a little more simple in this class. Let's look at the next one where it's one away from being completely filled. Oh. All right, in a similar fashion, the group 11 transition metals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The copper, the silver, the gold, and the rhenium, right? So they're one away from having a full D shell. All four of them. They're just one. So close to being full and so beautifully symmetric. So as far as I can tell, all of them do this, right? They will take a prior S subshell electron, pop it in to fill, because they've got 9 D electrons. One more and it would have 10 and be perfect, right? So it pulls one away from the D subshell. Let's take a look at this. You ready? So let's look at silver. So silver's here. Woo! I can't see upside down very well. Silver's there. So the prior noble gas is, whoops. So silver's right there. So the prior noble gas is krypton. So it would be krypton 5s2 4d9 is what we would expect, right? This is expect. Don't write this down. 2, 3, 4, 5. Hund's rule. 6, 7, 8. Now that's what we would expect from the output process, but no. Right? See, this is symmetric. That's not. Do you see that? So if it takes one away here, that's still sort of symmetric, right? And we pop it into here. Oh, so happy. Lower energy D subshells are half filled or completely filled. So we get the 5s1, or you could do this. Krypton 5s1 4d10. This is true for copper as well, gold, and rhenium as far as I can tell on that particular one. So exactly the same reasoning for the ones that have 4 D electrons that want to become half filled. Yay! Let's look at some trends on the periodic table and we'll be done, gang! All right, to end this off, let's take a look at some patterns, right? So remember what Mendeleev did. He put elements so that they had similar chemical behavior in columns or groups or families, right? So you got the halogens, noble gases, alkali metals, alkaline earth metals, pnictogens, chalcogens, all that. And he goes, wow, they got similar chemical behavior, but he didn't know about electron configurations or even electrons for that matter. But what we define now, let's connect it. We know the number of valence electrons in the outer shell is what reacts first. So that's what determines the chemistry of the element, not the total number of electrons, the number of valence electrons resulting from how we distributed all of the electrons through the orbitals. So wouldn't it be consistent to say any two elements or any elements that have the same number of valence electrons should have identical or nearly identical chemical behavior? Would that be a logical statement? Which means if we pattern them into columns with similar number of valence electrons, they would be patterned in similar chemistry. So from that conclusion, all the elements in the same columns should have the same number of valence electrons. And this is why I like doing the 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, because that's the number of valence electrons. 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5 valence electrons, 6. All the halogens have 7 valence electrons, and all the noble gases have 8. It's a thing of beauty. Let's look at one trend. All right, let's polish this off with some trends. I took the group 2A, the alkaline earth metals, beryllium, magnesium, calcium, strontium. I could have kept going, but I ran out of room. And I took group 7A, 1, 2, 3, 4, 5, 6, 7, the halogens, fluorine, chlorine, bromine, iodine, and I ran out of space. I could have kept going down. All right, and that's why I like this old numbering system. Well, if we do the noble gas core electron configurations, right? You just draw the prior noble gas, right? Just do the prior noble gas and then put the electron. So this would be helium 2s2. And then neon 3s2, argon 4s2, krypton 5s2. Notice they have exactly the same number of valence electrons. They all have 2 valence electrons. And it's group 2a. You see the pattern there? You see it? You see it? And then with the halogens, you do the prior noble gas, helium. And then you'd have the helium 2s2, 2p7, right? And here I did it as the noble gas core orbital box diagram. So you see the 1, 2, 3, 4, 5, 6, 7. They all have 1 unpaired electron. So these all, fluorine, chlorine, bromine, iodine, helium with the valence electrons, neon core, argon core, krypton core, they all have 7 valence electrons and all have 1 unpaired electron. They all have the same chemistry. It's an awesome thing, guys. And these, if you did the noble gas core with the boxes, you'd see these are all paired up. So they have similar magnetic behavior as well. Awesome stuff, gang. Keep it up.